Good afternoon, everybody. Thank you all for sticking around. I know it's been a long day of thesis presentations. I want to say congratulations to all of my other seniors. You guys are all tough acts to follow, so congratulations. My name is Brynna Downey, and my thesis advisor was Drac Wisdom. And the goal of my project was to find the location of Planet 9. Now, I must be completely honest that this is not a wholly accurate title for my work. Something that would be more accurate is more like this, where I wanted to find the most likely orbital position of a possible distant giant planet with a proposed physical and orbital parameters, with a strong emphasis on if the planet were to exist. Which might lead the question, Brynna, why did you do your thesis on something that might not exist since there's no observational evidence for it? And I would like to say I don't know, but there is some evidence that it exists. And for that, we have to look at the history of discovery of planets in our solar system. In fact, several were not observed before they were predicted. In fact, all of them except for Neptune and Pluto were observed first. But Neptune was discovered because Uranus was discovered to have irregularities in its orbit. These irregularities were caused by what was thought to be a gravitational mass beyond Uranus, and calculating the difference between Uranus's actual orbit and what it should have been given the other planets in the solar system, they were able to figure out where Neptune would be. And in fact, Neptune did not explain completely the irregularities in Uranus's orbit, which led to the discovery of Pluto. There was a lot of time in between these discoveries. I think Uranus was discovered in the 1750s, but then Neptune came in the 1840s and Pluto later in the 1930s. But we have a theme of being able to predict mass in our solar system based on its effect of other bodies in the solar system. So now we're going to fast forward to 2014, and it was discovered by Trujillo and Shepard that Kuiper belt objects share orbital characteristics. So we're going to need some background knowledge on Kuiper belt objects. We have all the planets in our solar system up to Neptune. Don't mean to exclude Pluto, but Pluto is considered to be the largest Kuiper belt object. Neptune is at 30 AU from the Sun, and for reference, the Earth is at 1 AU. So that's the definition. The distance from the Sun to the Earth is 1 astronomical unit. Neptune is at 30. The Kuiper belt is believed to be from 30 AU up to about 50. And so what Trujillo and Shepard discovered was that Kuiper belt objects past 150 AU. They also added the constraint that the closest approach cannot be closer than Neptune's orbit. So all of these Kuiper belt objects clustered in certain orbital characteristics, which leads to slightly more background information on what exactly are these orbital parameters that we're looking for. It was shown by Kepler that all objects that orbit another body in our solar system do so in an elliptical fashion. So you can completely describe the motion of an object by the ellipse that it follows when it moves around the sun. So whereas for an actual person, you might describe the x, y, and z position plus the x, y, and z velocities, you have 6 orbital parameters that you can account for. And 2 of them describe the shape and the size of the ellipse, and 3 of them describe the actual orientation of the ellipse in space. And there's a final 6th one, which describes where exactly in the orbit the body currently is. So Trujillo and Shepard discovered that this omega, the small omega, is where the Kuiper belt objects are clustering. We call this the argument of Perihelion, because this Perihelion P is the closest approach to the sun. So they claimed that given going back, that Neptune and Pluto were discovered based on these orbital irregularities. Perhaps these Kuiper belt objects are doing the same thing because there is another planet. They thought that the planet would be at about 200 AU from the Sun, and they would force this clustering by a kind of a resonance, a Kozai mechanism. It's like, okay, that's a theory. So then last year, Batygin and Brown stepped in and said, okay, we like this theory, but we think that the Kozai mechanism might not be the full explanation. And so they ran simulations to see whether they could say, given these parameters of a planet 9, would this create clustering in the Kuiper belt objects? And it turns out that they did. And so this is the summary of the features that they got. You can see that the planet 9 would be very far from the sun, very high eccentricity, very high inclination. And its orbit with relation to the other Kuiper belt objects would be that they would orbit in the same plane, but they would be 180 degrees off from each other. So the direction of farthest approach for planet 9 would be the direction of closest approach for the Kuiper belt objects. All right, and what we'll notice is that they're able to constrain 5 out of the 6 orbital parameters. And that's where I come in. My job was to find the 6th one, this F here in the picture, the true anomaly. So where exactly planet 9 is in its orbit right now. Before we continue, are there any questions? I think I'm clear so far. Nope. Okay. So, I should let you guys think a bit more. Right, so there have been several other attempts to find the true anomaly of planet 9, and we'll discuss the results of those a bit later. But what inspired us was a statement in Batigan and Brown's paper saying that they rejected 7 of the 13 possible Kuiper belt objects from their simulations because they were deemed too unstable. They were considered to be unstable because Neptune was interacting with them too much, it was perturbing them. And so they just didn't include them. These were considered to be unstable over billion-year timescales, so that's pretty long. And furthermore, they only consider Kuiper belt objects with a perihelion that did not come closer than Neptune. All right, and so this didn't sit quite right, because you would think that since the solar system is 4.5 billion years old, everything that is currently in the solar system is there because it's stable. If it were unstable, it would have been ejected already from the solar system. And so if these objects are made unstable by Neptune, perhaps they are stabilized by planet 9. And so that's the main idea driving the methodology in my project, was that planet 9 could stabilize the objects in our solar system. And in fact, a bit further, the exact location, the exact true anomaly of planet 9 would be the most stable configuration of the solar system. How do we do this? We do numerical simulations, and the thing that we varied was the initial true anomaly of planet 9. Planet 9 has a period of 15,000 years, so we can assume that the initial conditions taken a year ago, it's probably in about the same place that it would be this year. All right. So now for some dry information, but we have fancy fonts, so we'll get through it. I did n-body simulations over 100 million years, took the 8 planets, 26 Kuiper belt objects. They were treated as point masses, and then we took one planet 9. Batigan and Brown estimated that planet 9 would have about 10 Earth masses. Neptune has 17 Earth masses, so that's okay. Order of magnitude correct. We did this 20 times for 20 different true anomalies. The true anomaly ranges from 0 to 360 degrees, so there's 18 degrees per thing, right? Okay. And then the program outputted the position of all 26 Kuiper belt objects. Whew, okay, so now how do we determine the stability given the position of the Kuiper belt objects? Well, one thing you can look at is the eccentricity. You would like to think that the eccentricity does not vary too much over time if you have a stable Kuiper belt object. And keep in mind that I had 26 KBOs and 20 true anomaly values, and I only have 3 plots here, so I've cherry-picked them for a point that I would like to make, which is that these 3 plots have a clear stability order, but it was not so clear given all 520 or so plots that I had. This plot has a pretty stable eccentricity. There are some shakiness here. but it doesn't, from the starting point to the ending point, the eccentricity doesn't vary too much. The middle one, there's a big jump, but it comes back down. I would call it stable, stable-ish, ish being a technical term. And on the far right, there are jumps, but the eccentricity doesn't come back down. I think that if we had integrated this a bit longer, that the objects would have been ejected from the solar system. And I would call this one unstable. All the other plots were not, oh, sorry, yes?
Would ejecting from the solar system just not, what would that show up as?
Oh, right, so eccentricity of 0 is a circle, you're confined, you're not leaving. Yeah, if it goes to 1, it's a parabola at that point, and it's leaving. Right, so it was never this clear. And so we need, when one method doesn't work, you have to look for anything else to do. So this brought us to eccentricity versus semi-major axis. What we're looking for stable Kuiper belt objects is to have the orbit be in a fixed area on the plot. We see this on the leftmost one. The orbit stays in this tiny little corner here. The middle one, stable-ish, it starts off in this corner, but then it smears out to a different corner. And then on the far right, it has no confined area. Yes?
So what's the time scale that's these are 100 million years?
Yes. So after 100 million years, what is its behavior? Right. And yes, it's hard to know what the time is for each of these plots. So again, sometimes it was hard to tell if you had a slightly messier area, was that more unstable, less stable? Again, it was a little too qualitative for Brynna's bias. So we needed something that was me-proof. We needed some numbers, and that brought us to a numerical measure of stability, which is Lyapunov exponents. So unstable objects are chaotic, meaning that they depend very heavily on initial conditions. And in fact, they're so dependent that if you change the initial condition by a tiny amount, d0, you should see exponential divergence between the original trajectory and the resulting trajectory. So with time, the distance gets very, very large. And this is, the characteristic exponent is lambda, the characteristic Lyapunov exponent, given by this equation. And so what you can now do is you can go back and you can perturb all of your Kuiper belt objects by a tiny amount, and then you can calculate this number. I should specify that a smaller Lyapunov exponent is a more stable trajectory, but a larger Lyapunov exponent is a more unstable one. So we had to do another round of simulations. Everything was the same, except that we changed the Kuiper belt object initial conditions by 1 times 10 to the minus 10 AU. That's about 15 meters. And we had to do this 3 times for the x, y, and z coordinates, because there can be asymmetries in your phase space. What's important to note, though, is that if you were to perturb your object in any random direction, the Lyapunov exponent that was largest for these 3 coordinates would dominate. So what you can do is you can calculate all 3 and just take the largest one. That brings us to these graphs where you can see what the actual divergence looks like. We have the log of the trajectory divergence on the y-axis and time on the left, on the x-axis. These are straightish lines confirming that the orbits do exponentially diverge. The slope of the lines are the Lyapunov exponents. That's what I extracted from these graphs. And you can see, so these all have the same time scales. After about 200,000 years, they diverged very quickly. So that's about e to the 0. They differed by about 1 AU. So that's a lot. And confirming the hypothesis from before that the left was the most stable, middle was stable-ish, right was unstable. We can see this here in the plot that we have the smallest slope, next largest slope, and then the greatest slope. Right. So we can do this now for every single Kuiper belt object and true anomaly value, and we get graphs. I recommend squinting at the graphs so that you don't get too confused by them. What you'll notice is that there are no patterns except for along the Kuiper belt object. which I have labeled as TNO because I was not very consistent with notation. A TNO is a trans-Neptunian object, and for the sake of this thesis, it is the same thing as a Kuiper belt object. Right, so we have the number, which is just the index in my list of Kuiper belt objects, and there are some objects which are consistently unstable and some which are consistently stable, although there are points where a stable object suddenly became unstable. More yellow means more unstable, more blue means more stable. Any questions on these plots? Oh, okay, many hands, yes.
So how are stable and unstable quantified?
Yes, I have a threshold of minus 8.5 log units, above which you are considered unstable. So meaning if you are less negative, you are considered unstable. If you're more negative, you are considered stable. Remember, it's the log, I took the log of the largest Lyapunov exponent. So if it was a fraction, you took the log, it would become a negative number. So more negative, more stable, less negative, more unstable. Yes?
So does this include the 13 objects that they said were unstable, plus another bunch of objects that they said were stable? Batting in the ground.
Right, so
Do you have in the second part of that?
Right, because I have 26 Kuiper belt objects, but they only had 13.
Right.
I think that that's because they had the limit that the object had to be past 150 AU, but its perihelion couldn't be less than 30 AU. They didn't want Kuiper belt objects that interacted with Neptune, but I did not have that constraint.
So you're expecting all of them to be unstable, but they would have predicted all of them.
They would have, right. They would have predicted them all to be unstable.
So you're seeing something stable.
Right. I do not have their full list of Kuiper belt objects that they used, so it is hard to compare exactly which ones they deemed unstable and which ones I deemed unstable, but that is something which I should reach out to them for. Right, which brings us back to, we can see patterns along a Kuiper belt object, but you cannot visually see a pattern along the true anomaly, which means that we need another method, or rather we can average across. You can average across all Kuiper belt objects to find the average Lyapunov exponent for a true anomaly. The lowest one should be where planet 9 is. And that brings us to these plots. We're going to look first on the right. This is the crux of my thesis, that this dip here between 162 and 198 degrees means that this has the lowest Lyapunov exponent average, which means that this should in theory be the most stable interval of true anomaly values. This is the most likely region for planet 9 to be. And then another interesting thing to think about is how do the actual Kuiper belt objects behave? So again, I mentioned that we had an instability threshold of minus 8.5 log units. I've plotted this across, and I have the average Lyapunov exponent for every object, but then I've also included what the Lyapunov exponent would have been if there hadn't been a planet 9. So again, going back to the idea that planet 9 should make the solar system more stable. So did planet 9 make these objects more stable? And the answer is that for the unstable ones, it didn't really matter. You can see some dips here where the stable objects were slightly more stable without planet 9, but we can justify that a little bit in the future. So this showed that there is some difference in the behavior between stable and unstable objects. So let's take this plot and divide it into stable and unstable. That's what we get on the left here. And we find that stable and unstable objects prefer two completely different true anomaly values. And this is not what I was expecting. But it kind of makes sense that you would want to make the stable objects more stable. And this is okay because the preferred true anomaly value for stable objects corresponds to the least stable true anomaly value for the unstable objects. And the reason I think that is because these are the unstable objects whether there's a planet 9 or not. So going back to what Patikin and Brown argue that Neptune is the root of their instability, then perhaps these unstable objects are made unstable by Neptune, and then Neptune is in a stable configuration with planet 9, and so therefore these unstable objects should also be unstable with planet 9. That was my reasoning for why the fact that the preferred trianomaly for the unstable objects lining up with the least preferred trianomaly for unstable objects is a sign that 162 degrees is perhaps more likely than 198 degrees in our interval here. All right, and then just for bookkeeping, we saw on this plot that there are some objects for which the run without planet 9 produced greater stability. And so I plotted all Kuiper belt objects in the middle. We have unstable objects up top and stable ones down below. Again, this is just the average log of the exponents. And you can see that the runs without planet 9 were always slightly more favorable than the runs with planet 9. But I would like to argue that this is not an indicator that planet 9 makes them less stable, because there is a concept of entropy, which has to enter with the Lyapunov exponents. You can, the sum of all the positive Lyapunov exponents can be an approximation for a certain kind of entropy in dynamical systems. And so I argue that the difference between these two lines is because when you take out a planet from your model, you are decreasing the entropy of your system. But then when you add a planet in, you're increasing the entropy. So this distance, this difference in the Lyapunov exponent is due to entropy, but the differences in the Lyapunov exponent within the planet 9 run itself is because of stability, is what I'm arguing. Okay, so with that in mind, we already said before, we think that the interval is between 162 and 198 degrees, and so let's compare that to other methods. So Brown and Batigan, they updated their paper to get, they said it was more likely for planet 9 to be at aphelion, which is the exact opposite direction of perihelion. So it's at its farthest approach from the sun. It's also the place in the orbit where you spend the most time. And so they argue that this is the most likely place to be. They also used other data constraints to rule out certain parts of the orbit. Finga et al., their interval was not quite in line with mine, but then Medvedev and Vavilov, their interval was in line with both mine and Brown and Batigan. So that made me happy. I should point out that Batigan and Brown have published this picture claiming that Planet 9 would be in the constellation Orion. This is after 1,000 years, it should be here, 2,000, 3,000 years, again showing just how long the orbit is. And well, I got that Planet 9 is in Lepus. Yay, with the help of Amanda Bosch, who helped me figure out the right ascension and declination coordinates. Right, well, only if you know your constellations very well, will you know that Orion is right above Lepus. So they're actually very close to each other in the night sky. And so this made me happy because they corroborate each other. All right, I'd like to thank Jack Wisdom for his help, Jane Connor for all of her support and encouragement, and Amanda Bosch for the right ascension and declination coordinates. Any questions? So please.